Hello everybody, welcome back to my YouTube channel. In the last video, we discussed what masked multi-head attention is and what cross attention is. So now that we know every component of decoder, let's discuss decoder's architecture in detail so that we are done with our transformer architecture completely. We have already covered encoders part. I would highly recommend you to please go and watch that video because there we have covered not only the components but what is the intuition, what is the reason that why do we have these components and what they are doing together. So, for example, that why we are adding the inputs back here, why do we have a feed forward neural network? Those same concepts apply in our decoder part as well. So I will be covering everything in summary, but believe me, everything has been covered in detail in the past videos. So let's start. So let's say we are doing machine translation. We have a sentence in Hindi that is going in as input and the output that we get is a sentence in English. Okay, we are doing translation from Hindi language to English language. So, whatever sentences you have in your output, let's say you have a sentence here, and the translation of it in English is I love apples. Okay, so whatever output sentence you have here, mm, the first thing that will go as input, what it will be. So, you don't So how do you do it in encoders? That you take your input sentence, you tokenize it, then you produce its word embeddings, right? And then you find its positional encoding for every word, and then you add that encoding with your word embedding, and then you get the final vector that goes as input in your encoder. We discussed that in encoders video, right? So same way here, the entire process is same. You have your tokenization happening, you have your word embeddings getting generated, and then you have your positional encoding vector that is being added inside your word embeddings, and the final vector that you get that goes as input in a decoder block. But there's a catch here, you are doing one additional step here, and that is you are shifting right. What does that mean? That rather than passing this entire sentence as it is, you are just doing one additional step here, and that is you are adding a token here at the very start. So instead of sending this as input, you are sending this as input. You are just adding one additional token and you are shifting the entire sentence to the right of it. Okay. So this is what shifted right means. And why do we do it? Because this tells our decoder that it needs to start processing now. Okay, once encoder is done with its processing, now it's decoder's turn to do the processing and produce the final output. Now the inputs that we get here that goes inside our decoder block, and the first block that is encountered by our input vector is masked multi-head attention. And we covered this in great detail in our last video, so I'm not covering what it means, but I'm not covering what it means in detail, but to summarize everything so that even if you don't want to watch that video, you can still continue with this video. So basically, you already know what multi-head attention is, right? You have multiple self-attention blocks, and each what a single self-attention block does, that it takes in your word embedding and it produces contextual embeddings that are more contextually aware. Okay, now masked multi-head attention goes one step further and it says that at the time of training, you know what your output sentence is. But when you are predicting at the time of inference, you will not have your entire sentence, right? Because you are testing it. You will only have your input sentence. You will only have your Hindi sentence. You will not know the translation of it. That is why you are using transformers to produce the output, right? So at that time, you will have just one word at a time. So let's say at time step t equals to 1, our transformer produced I as output, and then love as output, then apples as output at time step t equals to 2, and then t equals to 3, right? So what we are saying here, that at the time of inference we will not have the knowledge of entire sentence, right? So our contextual embedding shouldn't depend on entire sentence, because that will be like cheating, right? It should be only dependent on the words that has been predicted up till now. Okay, so if we are at time step t equals to 2, so whatever words have been predicted up till now, our contextual embedding should only depend on that. That is why we use a matrix that is added, which is nothing but a matrix of minus infinities and zeros. And when we take the softmax of it, all those weights that are associated with the words that are not predicted yet, those weights will become 0. So ultimately, whatever contextual embeddings we will get, those contextual embeddings will be only dependent on the words that have been predicted up till now. Okay. Now, whatever contextual embeddings we have got from here, we add our input back into it, and we already know why do we add our inputs back. We discussed this in our encoders video. We then normalize the vector, and that output vector that we get from this block, that goes inside our cross attention block. And why do we say this block cross attention? Because we don't have a single input here. We have one additional input that is coming from our encoders block, the final encoder block, right? So there are two inputs here. One that is coming from, let me highlight this, that is coming from here, and second output that is coming from here. Okay. And what is happening inside here, that we are finding out embeddings in a manner that tells you that how much our input vector and output vector are related. So let's say I am finding out the embedding of I. So I will not find embeddings with respect to other words of that sentence. We will find that how much our word embedding is related to our input tokens. Okay, so instead of having something like contextual embedding of I depending on contextual embedding of word embedding of I with its associated weight, right? Instead of something like this, what we will have embedding of I, but that will be dependent on, again, there will be weights, associated weights, but what will be the product, what will be its product with, what will be, what it will be multiplied with, it will be multiplied with the word embeddings of this input that you are getting. Okay, so it will be मुझे सेब पसंद है. This is what our Hindi sentence will be for I love apples. Okay, so what we are saying here is that the embeddings that we are getting after this block, cross attention block, those embeddings actually tells you that how much our outputs and output embeddings dependent on our inputs. Okay, how related they are. And that information is necessary, right? In order to generate this word embedding or this embedding, how much our input vectors are playing role. And this is what we were doing in attention mechanism, right? When we discussed Bandana's and Luang's attention. So it is actually replicating that. We covered everything in detail in last video. You can go, I would recommend you to please go and watch that video. So the output that we are getting from here, again, we are taking the input, we are adding them together, normalizing them, and that final vector goes inside our feed forward neural network. Now, what this neural network does, as I told you in the last video, that it finds complex patterns that are there in our data. Okay, so since we are finding how much related our output embedding is with our input embeddings, so what this feed forward neural network will do, that it will try to find out complex patterns or relationships between them, okay, that are previously that our previous part failed in. Okay, basically more complex patterns it is trying to capture. And once we have got the patterns, we again take our inputs, add them together, normalize them, and then we get the final output. and that output then goes inside our linear neural network layer, which is nothing but kind of aggregating your outputs, and then we are passing it in our softmax layer. Our softmax layer gives you the l- gives you all the probabilities that are associated with each word. We pick the word with the highest probability, and that is what our output is. In this case, it will be I. Now, what will happen at the time of inference? At the time of inference, at next time step t equals to this I will go inside our encoder block. I mean the decoder block. Okay, so at the time of inference, your encoder block remains the same, but our whatever we discussed in the video of encoder, everything remains the same. Entire processing happens the same way at the time of inference as well. By inference, I mean prediction when we are testing our transformer model. But our decoder model, it unfolds in time. It unfolds in time. Okay, it's a single architecture, but at every time step, we are taking the output and we are passing that as input so that it can produce the next output. So what will happen? That we will send start from here at time step t equals to 1. It will produce I. Then this I will go as input back in our decoder block. Processing will happen. It will produce the next token that will be love. And once we have got our output, we will pass that as input in our time step t equals to 3, and we will get the final output apple. So that is how it happens at the time of inference. Okay, now we can have an additional token at the end, which is like this, that tells that now we need to stop processing. Okay, so I hope things are clear. If you still have any doubts, then do let me know in the comment section. You can also reach out to me on LinkedIn or Instagram. I'm also available there, always ready to help you in the best possible manner. And one additional thing that I want to discuss here is that what GPT and BERT models are. So these BERT and GPT models, they are dependent on transformer models. As you can see, the last T, that last T represents the transformer models. So if you take encoders only, if you take all your encoders together, if you take all your encoders together, you stack them one over the other, just like how we have in our transformer architecture. Then you send your input sentence, you get your output, right? So this is what BERT is. So BERT is nothing but stacked encoders. That forms your BERT model because you need language understanding there, right? And what is GPT? GPT is nothing but stacked decoders. Okay, this is stacked decoders because what it is doing, it is generating output. Okay, so I hope things are clear up till here. And in the next video, we will see what we can cover. I'm thinking of starting RAG because I feel that in 80% of the use cases in a Gen AI are around RAG. So I'm thinking to cover RAG in detail. We will be covering most of the popular RAG models, for example, corrective RAG, self RAG. There are so many different types. We will try to cover them in detail. And thank you for watching this video. If you like the content, please give this video, please give this video a like and subscribe to my channel. Thank you so much.